Today's guest is Adam Karen from Qualcomm Incorporated, which makes the Snapdragon products that we cover in the course. Now, Adam received his bachelor's degree from Cornell ECE. We're proud to have him as an alum. He received his degree in 2006. And while he was at Cornell, he twice interned at Intel, first in circuit design and second in computer architecture, winning a distinguished co-op award from Cornell in the process. Now, after graduation, Adam joined Intel, where he held a number of leadership positions, including his last one in which he managed a team that analyzed the competitiveness of Intel's current tablet and smartphone products, work that strongly influenced Intel's product directions in those areas. Now, since March 2013, he's been a senior manager at marketing in Qualcomm for the Snapdragon product line. And Adam, thanks for taking the time to speak with us today.
It's a pleasure to be here.
So first, I'd like to talk a little bit about your own career. So how you, first of all, got interested in ECE, electrical computer engineering. Did that happen when you were at high school, or is that something that happened while you were here at Cornell?
That happened in high school. I knew when I was applying to Cornell I wanted ECE, and it really happened because computers at the time were changing everything we were doing from our day-to-day activities, and I knew nothing about what was going on inside. The processor was just a magical black box, and this was kind of something I really wanted to learn more about. I took computer science in high school. We did some programming competitions with local universities, and that's really what got me hooked.
So you say you did some programming, but did you learn anything about hardware when you were in high school? So programming, a lot of people think about doing computer science, right? But you ended up doing ECE. So how did that come about?
I guess programming kind of opened the doors as to, okay, this is the language the computer speaks, but how does it actually, what does it do with this, or how does it do it faster? So really didn't have any hardware exposure in high school, but I was kind of the kid who would always take apart my parents' old electronics. So not a formal education with hardware, but that's how I got started.
Now, you worked as an intern and as an engineer when you were at Cornell. You worked for Intel. But then you kind of quickly moved on graduation into the business side. So did you kind of plan all along to go into business, or is this something, again, that happened while you were studying here at Cornell?
So that transition was not planned. I had actually intended to remain an engineer for the foreseeable future. But the way this transition happened is I joined Intel's rotation engineer program, which is their way for incoming students to try 3 different jobs in the company within the first year at the company to give them a broader range of experiences. And I figured I had done the hardware design with Intel first. So one of my first rotations I tried was software research with a bunch of actually Cornell PhDs were on the team. And then I decided to try something completely out of left field. Let's try marketing, which, to be honest, going into it as an engineer, I didn't have the highest regards for marketing. We kind of teased that field as a bunch of PowerPoint engineers. But what I learned from that rotation, it was in the competitive analysis group of Intel. It was still a very technical group of people. You had to understand your company's products and features and future capabilities, as well as your competitors. And you got the big picture of a product, big picture of the company and the industry. Whereas when I was on the circuit design side of things, I just had my little section of transistors, didn't know anything else about the chip, or in some cases, what the whole group was doing. So I really like that big picture and kind of the fusion of having to leverage all my engineering experience, but combining that with the business and marketing knowledge.
Now, it's interesting that you got into business after getting a bachelor's in ECE. So looking back, Cornell has a business degree. You could have gotten a business degree. So what do you see as the advantages and disadvantages of pursuing business with an ECE degree versus getting an undergraduate business degree?
Sure. So I think it really depends on the industry you're going into. For anything high tech, I think it's extremely valuable to have that engineering degree, because every decision the company's making, the products they're making, all have engineering at the foundation of it. And just looking at, whether my companies I've worked for, from Qualcomm to Intel, founded by engineers. The current CEOs have engineering backgrounds. And no matter what you do, from the marketing to product management, having that technical expertise makes anything going on that much easier because you're that much closer to what's really going on with the company. That said, I do think there's some benefits to going on the business side, and some of these things maybe still be available to engineers. For example, I think your typical engineer has a very heavy workload and not as much time for some of the extracurricular activities that would help you on the business side, whether it's networking events, business plan competitions, and some of the experience you could potentially get if you weren't so bogged down in your latest physics assignment. So I think there is a balance depending on what students are going after. But if they're looking at high tech, I know many of my colleagues and even some of my Cornell fellow students, started with that engineering undergrad and then went for after a few years of experience in Silicon Valley, went for their MBAs afterwards and are just now doing a similar high-tech business role.
Right. Now, when you were here at Cornell, there is a business minor. Did you pursue a business minor? I forget from your CV whether you did. I think at least you took some business courses. Is that right?
Yes, I didn't take a business minor, but started taking some of the classes that were used for the engineering management minor. So I didn't take every single class. I didn't get the official minor, but was kind of on that track. And again, that was with the idea of managing a team of engineers and still being an engineer. So it wasn't until I had that marketing rotation that I made the full switch.
You managed to fit that in while doing all of your engineering courses.
Yes.
That must have been quite a feat. I know, well, a lot of students do that. I know it adds, I mean, there is room in the program, right, to do a business minor. Mm-hmm. Would you say it's more work to add the minor rather than doing other things, or how much more work was it for you?
I forget the exact credit hour breakdown, but I couldn't use my engineering management credits towards whether it was like my arts requirements and that sort of thing. So it did make for a fuller schedule. But for students whatever university they're at, companies, and if you're looking at MBAs down the line, other engineering programs, they always look for, how hard are they pushing themselves in the type of classes. And even I keep getting asked, what did you take senior year? And so luckily I actually took some 500 level, or I believe it or not, 5,000 level at Cornell for the graduate level architecture classes. So yeah, highly recommend keep pushing yourself on either side, the business or the engineering, even if you already have that job offer.
Now I want to talk a little bit about your design experience. So while you were in Intel, you worked on server chips. So you worked on the Xeon line, which is used for servers, and also the Itanium line, which is designed for servers. Now this course is about smartphone chips, or chips also that can be used in tablets. Snapdragon can be used in both. So can you talk a little bit about the differences in designing a chip for a server versus one that's supposed to go into a smartphone or a tablet? So differences in the architectures, the instruction sets, the microarchitecture, the design criteria, cost, performance, power, and the process of designing these chips. Can you talk about how they're similar and how they're different?
Sure. So I'll start with the similarities because that will be very quick to cover. It's basically at the high level, we just have a multi-core CPU system, and that's where the similarities really end. So on the server side, let's just start with how it's intended to be used and where it's going to be used. So these chips are selling for, in some cases, several $100s, and are running at have a TDP north of 100 watts, whereas
so thermal design point, TDP, thermal design point.
Yes. So yes. Oh yes, the acronym. Apologies.
No problem.
So another major difference are how these processors are used and where they're used. So a lot of server chips are going to be housed in a design farm or a server farm. They're going to be in an air-conditioned environments, and they're going to be plugged into the wall, while they're in use. Whereas with smartphones, these chips are in devices that are housed in your pockets. held in your hand and held up against your cheek if you're making a call. So there's a very different thermal design point for each of these. So beyond that, what they're actually computing, what they're calculating are very different use cases. So these server farms can be doing complex simulations, whether it's protein folding. Use some simple ones at Cornell for simulating the chips we were designing. And some of them even are used to predict weather patterns across thousands of kilometers. And they're doing this in the space of hours. Now let's go to your smartphone. That's measured in how quick can you open a weather app, in milliseconds. So very different types of programs you're looking at over in very different thermal budgets. And as I was saying earlier, that's also going to depend on how you design these things. When we were looking at Xeon, for example, one of the things we had to consider was error correction. So is there some cosmic radiation that flips a bit and could potentially corrupt your data or whole program, and have a cascade effect where all those hours of simulation are useless? That's something we had to design hardware for and have some backups ready for that. In smartphones, these are going to be much smaller area and not as concerned if there is a small floating point corruption in compared to a massive server farm.
So in the servers, you have to have some kind of redundancy, right, so that the system is always running, even if you get one of these, cosmic rays that produce a neutron that flips a bit in memory, for instance.
Exactly. And if you have to restart your smartphone in the rare case, it's not as drastic comparing to something like a massive server farm crashing because of that, or hours or days long simulation being thrown out. Other points on the server side, I think another thing is the design cycle for these products. With servers, it tended to be large quantum leaps over a several year period versus smartphones, at least in the US, where you have a kind of a 2-year refresh cycle with the carrier subsidies. People are expecting these phones to get better and better every 6 months. So with our crate line of processors, we weren't waiting for releasing one crate and then the next generation years later. There were smaller increments, smaller improvements, but at a much faster turnaround time.
The first Snapdragon chips had a pretty simple processor, pretty simple graphics capability, camera capability, these kind of things, because given the area that you had and the transistor density, that's about all you could do at that time. Now, thanks to Moore's law, we've got a lot more transistors on a chip within a given size chip. So can you talk a bit about how Snapdragon has evolved in its capabilities and its performance since the initial offering up to what you offer today?
Sure. So it is a night and day comparison. I'm sure anyone watching this class they may have heard of the first Android phone. This was the HTC Dream, but they probably didn't use it themselves. But to give you some specs of what was capable then to what we're capable of now, that first phone was about 3 megapixel camera, and now we're capable of 55 megapixels. And that's so people are clear, it's not just about that little lens on the back of your phone. We have dual image signal processors in there, capable of up to over like a gigapixel per second to process all those high resolution images. And so that's silicon and die space used to do that.
Now these signal processors are specialized processors, right, that you've designed specifically for this function.
Exactly. And other examples, so on the performance side, it's a night and day difference. I believe the first Qualcomm chip in that phone was probably 500 megahertz. We're now pushing past 2.5 gigahertz. And other examples, I think this first phone didn't even have sensors. So people today, you rotate your phone, the display changes. Simple things like that didn't exist. You had 0 sensors, now you have north of 7. The latest Galaxy S5 has a heart rate sensor built in. And in Qualcomm chips also have a sensor core, sensor engine to process input from that, the gyroscope, the accelerometer. They're even moving to pressure sensors to determine what level of a building you're on, what floor, because there's different altitude. Other examples, resolution. That first phone was, I believe, like 400 by 300 was the screen's resolution. Now our chips can support native 4K displays on tablets. And smartphones today, like the LG G3 I have, has a 2K display. And so that is a massive, massive amount of pixels we have to push to the screen and process, whether it's for gaming or UI, whatever the case might be.
Right, so it's not just a matter of having the resolution. It now demands a lot more processing when you increase the number of pixels to that degree.
More processing, more memory bandwidth. You need a lot more horsepower to drive those sort of use cases. And one other example I think people don't realize much about is the amount of satellites for global positioning that these phones can now handle. It started off where you would lock into one satellite, but now our chips can support multiple satellite constellations. For example, the European Union has its own set of satellites. The US or GPS has it. There's the Russian GLONASS system. China has its own set of satellites. And so when you can use all of these, you get a faster time to fix, a more accurate position, and all of these things are things that are happening under the surface, but people don't realize it's tied to the SOC and to the silicon.
Now you mentioned the clock frequency change in the processor from 500 megahertz to multi-gigahertz. But you've gotten performance not just from frequency change. I imagine we talk about parallelism in this course and how you get performance from increased parallelism. I imagine that the level of parallelism you're able to exploit, instruction level parallelism, is also improved from the first generation to what we have today.
Oh yes, even from I think the first, we're now at multi-core systems, but this also goes to the scheduler. The software scheduler. We will work with Android in some of these cases to make sure you're able to more accurately schedule the right thread on the right core and determine if one core is too busy. But yes, that's something that's improved greatly since the very first Android phone as well.
Now you just mentioned that you have different cores on a chip, right? So you have a typical Snapdragon processor. You've got a bunch of general purpose cores. Plus you have all of these specialized processors for doing graphics, doing video, audio, all these kind of things. Now, I want to talk a little bit about why that's the best way to design an SoC for a smartphone or a tablet. So theoretically, you could have just a few very powerful cores that could handle anything, rather than have all of these, some general purpose cores like you have, plus a bunch of specialists. So why is that general purpose cores plus specialist approach a better approach for these kind of chips rather than having a few very powerful cores that are generalists that could handle all of these different tasks?
Sure. So it's really a question of what type of efficiency are you after. Having the more general purpose cores, you're much more efficient in terms of the die area, but in mobile, the power and battery life is king. So once you have these specialized cores, they are typically able to do a task much faster in some cases, or at much lower power than a general purpose CPU, or both. So one of the examples, again, folks might not realize this as well, is with Android KitKat or 4.4 with the Nexus 5 launch. That's using our Snapdragon 800 processor. Google touted 50% longer audio playback. Excuse me. And that's because when you're listening to your music with the screen off, rather than having to wake up the CPU to play that music, it is going straight to the DSP or digital signal processor and through what we call audio tunneling. So you're on the bus listening to your music, not touching your phone, grocery shopping, listening to music, whatever the case might be. That's a huge savings in power because it's now not using the CPU. for that use case. Another core that's much more efficient at doing that, doesn't have to wake up the higher power CPU. Same is the case with sensors. Now that sensors are enabling a lot of what we call always on use cases, meaning they're always doing something, whether or not you're using the phone. Think of something as simple as a pedometer, measuring every step. You don't want your CPU to wake up every time you shift in your seat or take a step. You want the lower power cores to be processing that information. So you could be measuring your steps all day and still have plenty of battery life left.
Now, I imagine there's some applications where a lot of these processors are just sitting idle. You're doing something, one task, and so a lot of these are just sitting idle. And you have the capability, though, to kind of turn them off. Is that right? In order so that they're not burning power. So how does that work?
So for some of these devices, you can even turn off CPU cores if they're not in use. One of the things we had custom with Crate, again, this is just on the CPU side, is we could change the frequency independent of each other core. So that's to minimize power as well. But the other cores, if they weren't actively in use in the first place, if you don't have your camera app open or something that's not using the camera, it's the ISPs aren't necessarily awake, so it's not necessarily that it needs to be actively managed in that case. But depending on,
and the ISP is is one of the signal processors.
Image signal processor, yes, yes. So in this case, yeah, once the task is done on a given processor, the CPU, I guess, facilitates in, I don't want to say shutting them off, but there is power management for each of those blocks.
Now, there are other usage scenarios where the chip is really humming with activity, or the CPUs are working and these special processors are working. So can you describe a usage scenario or two where your chip is really humming with activity with all of these processors working? Also, you've got memory controllers and permanent storage where there's just a lot of activity. So what kind of applications really make that SoC hum with activity?
Sure. One of the cases we use for some of our power testing is actually much like what we're doing now, a video conference. So if you're doing this on your phone, the camera's going to be engaged, the ISPs. You're going to be connecting either through Wi-Fi or LTE, sending data back and forth. That component's live. Depending on what sort of, if it's a high resolution and you're using the HEVC codec or high efficiency video codec, we have dedicated hardware in some of the chips to encode and decode that codec to speed up the process and be more power efficient. Obviously this phone's display is on to look at the other person, so you have that part consuming power as well, and those require several different IP blocks or several different engines. Another one is depending on the type of gaming you're doing. Say you're online gaming, much like the video chat, you have LTE connected again potentially. If you're doing one of the racing games, as you're tilting the phone side to side, it's using the sensors as well, and obviously the GPU to process and push all those pixels. So depending on the usage, there can be many different IP blocks in play, but then there's also multitasking. So say I was actually playing a game while talking to my family because it wasn't an interesting conversation, whatever the case might be, I might be using different IP blocks for different things.
Okay. So how do you manage that trade-off between giving people good performance for their game or their video call while still giving them long battery life? What are some of the techniques, the engineering techniques that you use in the Snapdragon chip to address this kind of conundrum?
Sure. So every IP block has its own way of solving a specific one. One unique one, it has to do with the modem, because unlike desktops, I think the average user has a ton of different apps, from news to weather to social to gaming, and each one of these apps might be trying to phone home, so to speak, out of sync with one another. But to do that, you're not even using your phone at this point. It has to wake up potentially the AP or the modem, connect to the web, download that information, shut off, and then another app's doing that, and another app's doing that. One of the features we have kind of aggregates all of those requests, so there's only one connection to the internet to phone home, get whatever those updates are, and then shut down. So that's just on the modem side, and there's several examples within modem doing that. Uh, we've even taken a software approach in some cases. We released an app called Snapdragon Battery Guru that will know how you use your phone and where you use your phone. There's some contextual awareness. So, for example, when I'm at my home, it knows I'm connected to Wi-Fi. Whereas once I leave the office, it knows I'm not connecting to any hotspot. So rather than having my Wi-Fi on all day, searching for a signal, wasting power that it's not going to connect to, once I leave leave my home, it knows to shut off the Wi-Fi. So there's different approaches to shut off different units or minimize when the units are active. And every IP block has an example of this. I'll give one more on GPU. So there's different ways to render the type of what pixels are on screen. One of which is direct rendering, one of which is deferred rendering. And depending on the scene, depending on how much activity, depending on the vertices versus pixels, all these different things, one might be more efficient than another. Most GPUs today are either doing one or the other, whereas our Adreno GPUs can do both, or what we call flex render. So depending on what's best for a given moment, a given scene, it can dynamically switch between the two. One might be delivering higher performance because in, like, say, a first-person shooter, every frame per second counts. Whereas a slower game, you don't need that higher frame rate. Maybe a different rendering mode will save power. So there's many different ways to do each of these trade-offs, and each IP block handles it differently.
So it seems like, and I've talked about this with other guests, that one of the kind of keys to energy efficiency is to be aware of what the chip is doing. The task that's being done, or what kind of activity is happening, and to kind of dynamically manage this as the program is running, as the application is running. Is that true? I mean, it seems like the GPU example is a perfect example of that.
Yes, exactly.
So can you talk about, as far as I understand, Crate has never included SMT. So you guys made a decision. You certainly had the technical know-how to include that within your chips, but you made a decision that it was best not to have SMT in Crate. So can you give us a little insight as to why you didn't do that? Why you didn't include SMT?
So I couldn't speak exactly to the engineering thought process from our architects, but at least at the high level, similar to what you asked previously on the trade-offs between die area and efficiency, and like our server talk about power versus performance. Engineering at its core is deciding which trade-offs are acceptable for a given product. And for mobile, since again power is one of the biggest concerns of the average user and the OEMs building these phones, so there's ways to get more performance, but they're not always worth some of the negative sides, the side effects, or the negative trade-offs. And so given the focus on power and designing these chips specifically for mobile, I think that's why SMT hasn't been as popular on this side. Even looking at recent Intel chips, their Atom line started off with SMT, I believe. But then their newest generation and CPU architecture has since gotten rid of that. So, they started off wedging a desktop background, something that was designed for desktop, into mobile, but have since started to tailor it more for the mobile market.
Now, you've moved in Snapdragon to 64-bit computing. Previously with Crate, you had, which was a 32-bit architecture, so the size of an integer was 32 bits. So now you've moved to having the size of an integer being 64 bits. So can you talk about the advantages that users will see with 64-bit computing, or what they're seeing right now, because you offer that right now? So are there particular applications where they'll really see a boost, or is this something that they'll see just generally across everything that they do with their smartphone?
Okay. So there's three main parts to that 64-bit story. So Qualcomm is now providing the 64-bit chips. Google has just now released Android Lollipop, which is their first 64-bit operating system, and that's not on pushed out to every phone yet. But then the final component to that are those 64-bit apps. So not all three pillars are in place right yet. This is still the very early phases of this 64-bit transition to mobile. So I don't have any good examples of naming an app that doesn't exist and seeing X amount of performance gain. What we are seeing are in the performance gains from 64-bit, are more on the synthetic benchmarks. But synthetic benchmarks don't always, represent what the user is doing, what the apps they're using, the usages they're seeing. So we're at that early stage where I couldn't tell you an exact usage, but we've seen benefits on everything from floating point and spec to JavaScript, which helps with some web browsing. But these are very, again, synthetic use cases.
When we say synthetic, these are benchmarks that you've created to test various aspects. Is that correct?
Yes, it's some benchmarks we do internally or create internally. Other ones are industry standard, where multiple companies create these benchmarks. And yes, when I say synthetic, they've created a custom test that isn't necessarily, it tries to reflect what real world use cases are, but it's not the actual use case itself. So again, that going back to the server example, Spec is designed for high-end CPUs, and Spec 2006 has a weather simulation subtest within it. But in your smartphone, again, you load an app that tells you what the weather is now. You don't care what it's predicting it, a month from now. So it's not necessarily reflective of how a smartphone user or a tablet user would use their phone. That's why, we're really anxious to see, once we do have that third pillar of the 64-bit ecosystem, when people start creating these apps, to see what sort of benefits we'll see. We've been talking about 64-bit as a way to future-proof, as you have the hardware component. Now as the operating system and app component come into place, you're not left behind. Another aspect of that is addressable memory. Right now, most smartphones and tablets are, they're all 4 gigs or below. So you're not getting the benefit of addressing beyond 4 gigs at this point. But that's something that, will be happening, and I'm sure in the not too distant future.
Right, and that was part of the motivation for 64-bit computing in high-end machines, right? Is now we have addressing, it's very easy to address, have a higher number of addresses, and being able to very, very simply address a larger amount of memory. All right, so I want to talk a little bit about where you see the future going. So what new capabilities are you seeing on the horizon for SOCs like Snapdragon? And what are some of the technical challenges that are facing designers of future SOCs?
So as far as the future of these processors go, I think it's more where they're going that's going to be one of the challenges for designers. So much like the processors and CPUs move from your desktop into a phone in your pocket, now these mobile SOCs in your smartphone are finding their ways into wearables that are, whether it's a smartwatch on your wrist, they're being pushed into smart cars. Your car and your refrigerator are going to, potentially be communicating to one another in the Internet of Things. So we're talking about even smaller thermal budgets in some cases than what you have in your smartphone. And another different aspect is you're not designing as much a general purpose processor as one chip that does one thing very well. And that can be either in performance or in power, but it's not as all-encompassing, which can be easier, but also a challenge since you have to do that one thing so well. Another aspect, I think, is because most of these chips now are doing something very enabling an experience, where it's not necessarily the floating point performance that matters. Whereas when you're first creating these chips, years ago, you could design to that spec benchmark, and everything else would kind of fall into place. But now designing for a use case, a user experience, why a user should actually care, it usually it isn't measured in terms of some synthetic benchmark. So being able to simulate a synthetic benchmark is very easy. Being able to simulate how a user is using this device is much more complicated. So it takes a very different mindset, and I think it's a bit more challenging for the architects in the earlier stages to determine what trade-offs they need to make in order to hit that user experience as opposed to hit a given benchmark score.
So I want to ask you one more follow-up question about that. So are there other places, we think of Snapdragon being used in smartphones and tablets. So are there some other more interesting places where you find Snapdragon SOCs besides on your phone or in your tablet?
Oh yes. So today, for example, in most of the Android Wear watches that are available, they have one of our lower-end Snapdragon chips inside. They will also sell chips to the embedded space. If you look at, I think one of our keynotes last year, there's robots roaming around the stage, with Snapdragon inside. So, this is all outside of your pocket and smartphone and into, more specialized equipment. Some of it's wearable, some of it's embedded, and automotive is also something that's, I think, in the future for many chip makers. Now that these, whether it's smart driving cars, whether it's being able to have communications integrated inside, even built-in infotainment, as opposed to just a DVD player in the head seat, now you have a full embedded computer potentially. So there's many different places for Snapdragon and these sort of products to go in the future.
Adam Karen from Qualcomm. Adam, thanks for joining us.
Thank you for having me.